So in this practice, calculate the acceleration of a rolling solid sphere and find its speed when it reaches the bottoms. So question is very similar to the previous questions. But in this case, we use the equation of motion to find the speed of rolling spheres at the bottoms. So it's better to draw the free body diagrams at first. And actually, force acting on this object is mg, is a gravitational force, and the normal force, and the friction. These three forces acting on this object. The angle, this angle, theta. Okay. So these directions, we can decompose gravitational force directed downward and this direction in the parallel to the slope. This part is mg cosine theta. This part mg sine theta. Then we can write down the equation of motions. And first one is ma is acceleration. Ma equal mg sine theta minus f. Friction is directed opposite direction, f. So first equation. And second equation is a rotating. It's a rotation. Angular acceleration is alpha. So we can express the I alpha equal torque. This is R and F. So this is right angle. So again, this is R times F. This is torque is R times F. And the acceleration A is related to angular acceleration R alpha. In the case with the rolling sphere without slipping. Equation number 3. This is the equation of motion. And in the normal direction with respect to the slope, n minus mg cosine theta equals 0 because there is no motion. And the friction, this is equation number 4. Friction have to be the smaller than the mu n. This is equation number 5. Additional equation. This is the coefficient of the static frictions of static friction. Then we can use this equation. So from the equation number 2, you can find the alpha is R over I F. And then you can use this equation 3 with this equation. A, you can substitute this expression is R squares over IF. So from these equations, F can be expressed I over R square A. Then once you have these expressions, you can substitute into the equation 1. So equation 1 becomes M plus I over R squares A equal mg sine theta. So acceleration is expressed m over m plus I over r squares g sine theta. Then we consider the rolling spheres. So I is 2 over 5 mr squares. You can substitute this expression here. Then it becomes 5 over 7 g sine theta. So this is the acceleration of the rolling spheres. And then if you consider the, maybe it's better to draw the new figures. This is theta. This is h. If you consider this is L, this object is start falling and moving. Finally, it's come to this region, and we'd like to find the velocities. And we can use the distance L is related to accelerations 1 over 2 at squares. You can find the t. How long does it take for the ball to come to the bottom of the slope? Is 2L over a squared. From this equation, you can find the velocities because a times t. It becomes, if you substitute this t here, it becomes 2al. And then we have already discovered this is a. You can substitute here. It becomes squared 2 times 5 over 7 g sine theta L. And L sine theta, this part, if you consider this triangle, L sine theta, actually it's h. So velocity is expressed square root 10 over 7 gh. So this is the answer to these questions. And in the previous questions, we get the same answers. But in these cases, we can go further, a little bit more, using the equation 4 and 5. From the 5, we have some conditions for the without slipping. So for the n, you can substitute this expression here. So frictional force, also this F is coming from this expression. And this equations A is substituted here. So from the F is smaller or equal to the mu n, you can substitute n. N equal mg cosine theta. And the F, you can look at this equation. F equal I over R square A. So I over R squares. I over R squares. A, we have discovered this is A. So you can substitute 5 over 7 g sine theta. This is A. And if you substitute I equal 2 over 5 mr squares, this becomes 2 over 5m. Then you can calculate. This becomes 2 over 7 tangent theta, because g is cancelled out in both sides, and m is cancelled out in both sides. Is smaller than nu. So we have a condition for the theta. tangent theta have to be smaller than 7/2 news. So if you substitute the typical value of the nu, it's nu equals 0.5. It becomes 1.75. Tangent thetas have to be smaller or equal to the 1.75. So this, in this case, theta can be calculated about 60 degrees. So if the theta is really small cases, the rolling sphere is actually the rotating without slipping is possible. But once the angle is larger than the theta is larger than 60 degrees, actually object cannot rotating. It's going to slipping. Friction is not large enough. Okay, so this is the answer to these questions.